Physics is the most fundamental of all the sciences. All the other sciences are, when it comes down to it, just applied physics. Chemistry is the repeated application of the Schrödinger equation. Biology is the repeated application of chemistry. And geology is the repeated application of all three. Now, this does not mean that physicists know what on earth they're talking about when they go arrogantly strutting into other scientists' areas of study. Analyzing the causes of something like World War I by calculating the valence electron states of every single molecule on the surface of the Earth between 1914 and 1918 might technically work, but only if you had a computer bigger than the known universe. A much more efficient method of going about it would be to use established methods in fields like psychology, sociology, economics, and anthropology. Now that's the difference between the straw man of reductionism and my opinion of constructionism. The other sciences aren't detracted from by being applications of physics. The other scientists expand on physics into a vast world of emergent phenomena which are so complex, so beautifully intricate, that it is impossible for a physicist to use the methods of physics to understand them efficiently. Society needs separate specialists for all of these emergent phenomena because existence is just that awesome. Now, one of the biggest inputs the other scientists take from physics is Newtonian mechanics. So that's the paradigm I'm going to describe first. Now, technically, we shouldn't be doing this, because Newtonian mechanics is a dead paradigm which was overthrown by Albert Einstein over 100 years ago. But the best scientific theories, the really, really successful paradigms, never quite die. Like a champion thoroughbred racehorse, they get put out to stud instead. And the reason why we keep Newtonian mechanics around is because while it may not be perfectly true, and no idea ever can be, it is an incredibly good approximation to the truth. You see, it's only at speeds approaching the speed of light, or gravity approaching the gravitational pull of a black hole, that the differences between Newtonian mechanics and the truth become noticeable. And those types of circumstances aren't really relevant for the other scientists. You know, say a biologist isn't going to fire his lab rat through a particle accelerator. And so the other sciences use Newtonian mechanics as their takeaway from physics because it's incredibly close to the factual truth and because the math is a hell of a lot easier. Newton's first law of motion states that an object at rest will remain at rest, or an object in constant motion will remain in constant motion unless acted upon by an unbalanced force. This is what we call inertia, and it was the final nail in the coffin of Ptolemy's ideas, which had come down to Newton's time through the Catholic Church from Roman times, basically. And the old ideas had been that all solid objects that are in motion eventually come to a stop on the ground. However, this is because all the solid objects we see around us are on the Earth and in the Earth's atmosphere, and so they're subject to two unbalanced forces, gravity and friction. Newton's great insight was to realize that out in the vacuum of space, if you throw a ball, it will keep going in a straight line forever. Now, in fact, we now know, since the time of Einstein, that there actually is no difference at all between rest and constant motion. If Newton had had the courage to follow his ideas through to their logical conclusion, he might have realized that. But he didn't have that courage. Newton's second law of motion, number 2, states that force is equal to mass multiplied by acceleration. What this basically means is that the harder you push something, or pull it, whatever, the faster it's going to accelerate. It's kind of intuitive. It also says that if you push two objects with the same force, but one of them is heavier than the other, then the skinny object is going to accelerate faster, as demonstrated in this very badly animated cartoon. Newton's third law of motion states that for every force there is an equal and opposite reaction force. You can demonstrate that in the little cheesy cartoon I showed earlier with the rocket motor. Now, a rocket motor works by shooting out a bunch of hot exhaust gases downwards and resulting in the rocket shooting up upwards. Now, the rocket nozzle exerts a force on the exhaust gases, pushing them downwards, and the exhaust gases exert a force on the rocket nozzle, pushing it upwards. These forces are equal in magnitude, but since they act on different objects, they are not balanced. Now, finally, we have Newton's law of gravity. This says that any two objects, like, say, the Earth and an apple, are attracted to each other with a force that is equal to a constant times the product of their masses divided by the square of the distance which separates them. Which I'm going to call R, because usually this is used to solve problems involving planetary orbits, which are approximately circular, and R stands for radius. Now, if you're just doing that simple problem of just two objects attracting each other, it's pretty easy. However, the complications come because it's not just the Earth and the apple which attract each other. Because the Earth and the apple both attract each other, and they're simultaneously both attracted by the sun and the Andromeda Galaxy and Lenny Kravitz and the Dramatic Chipmunk and every single other atom in the entire observable universe. Trying to fully solve any gravitational problem is impossible. So what physicists do is they will exclude the vast majority of things which exist from their problems and only focus on the important things, on the things which are close enough and massive enough to matter for the particular problem they happen to be dealing with at the time. Now, Newton himself did not know why objects attracted each other gravitationally. He just observed that they did. And oftentimes scientific progress is made this way. A scientist will observe something about the universe, describe it, and then wait for another scientist to come along and explain why that actually happens. And that was the case with gravity. Newton had absolutely no explanation for why gravity happens. That would have to wait until Einstein came along 200 years later and developed a general theory of relativity, which I'm going to talk about in the next video. Stay tuned.